This is the third installment of Advanced J1939. This installment will discuss real signals versus ideal signals. I figured I probably better cover this because if I look at data which I take in the field, such as with an oscilloscope, or if I see data which somebody has posted from an oscilloscope, what I'm covering or what I'm going to show in much of the theory is going to be ideal signals. I do want to address first off, why we see things which are not ideal in the signal. This is real data which was taken with an oscilloscope in the field on a real machine. Nothing really wrong with the machine, it's just some data. I can see that can high and can low are being held in a recessive state at about 2.5 volts. The voltage differential between can high and can low is about 0 volts, as we expect. I can see then that I have a controller which starts broadcasting a message, and this would then drive the CAN bus to the dominant state, which is going to get us about 2.5 volts CAN high, or 3.5 volts CAN high, and 1.5 volts CAN low with respect to ground. After 2 dominant bits, we return back to a recessive bit, a couple of recessive bits in a row, and as we see the voltage decreases on CAN high, back down to about 2.5. CAN low increases from 1.5 up to about 2.5. So this is a pretty typical pattern of what I would expect to see. This is a real signal. If I were to discuss the ideal signal, it would be an instant increase from an exact value of 2.5 to some exact value such as 3.6 volts. It would remain at that 3.6 volts, and then a vertical line would show that an instant decrease in the voltage from 3.5 volts, 3.6 volts back down to the 2.5. Same thing on CAN low, but in the other direction. But if we look at this real signal, it doesn't have those characteristics. There is a period of time that it takes for the signal to both to increase on CAN high and to decrease on CAN low. We can see that this time is shown by how long it takes to go from here to here. So there's a period of time. It's very quick, but it is nonetheless a slope. Same thing for the on the drop back down to recessive state. There's a period of time for this to occur. We can see there's an angle to this. We can also see that there's what we may refer to as noise or oscillations. This is a ringing, if you would, that is occurring. So this is kind of an echo, I guess the best way to put it, that you can see that there's this pattern, this oscillation. This is, as I said, this is a pretty typical waveform taken from a real bus. I'd like to discuss why we see this and then why this is important. What causes this basically? Why does this occur? Why do I see this? And it isn't necessarily because there's noise present. This is being induced by the system or being created by the system. Part of it is the wire of the data link or of the CAN bus itself. I'm going to pull up a data sheet for SAE J1939-15 cable. This is the unshielded cable. You might not think that there would need to be a data sheet with engineering specifications for wire, but there definitely is for this data link cable. It's very important that we know a few electrical characteristics about it, because this is part of what causes this ringing, and this time delay that it takes for this to increase is the wire itself, which you might find to be amazing. The DC resistance, this is what you measure with your Fluke 87 or your Fluke 88, your multimeter. This is has a value or a nominal value at 20 degrees C of approximately 25 milliohms per meter. That means 25 thousandths of an ohm per meter. So if I had 10 meters of the cable, I would expect to be able to put my meter on there, and I might measure something around 0.25 ohms. My meter might not read volt or the resistance is that low because it is a very, very small amount of resistance, but nonetheless, this wire has resistance, and that plays a part in that ringing pattern that I showed. The propagation, we're not going to worry about that. That's the percentage of the speed of light that it takes the signal, the time for it to travel. It's 5 nanoseconds per meter. So nano is 10 to the -9th. That's how fast the signal goes. Not anything we need to worry about at 500K or 250K CAN bus. Characteristic impedance. This is something which is a very difficult concept to explain. The best way I can put it is it's imaginary. You cannot measure this with a meter. It is a combination of what is known as the inductive reactance and the capacitive reactance. So there's the wire is, even though it's a straight piece of wire, it is an inductor. And an inductor, you may know another name for it as a coil or a choke. So an inductor is the ignition coil on a spark ignition engine. That is an inductor. The coil that's in a relay, that is an inductor. But a straight piece of wire also has inductance. So that's part of this characteristic impedance. The capacitance makes up the other part of the characteristic impedance. It's kind of the opposite of inductive reactance. So capacitance is defined as two electrical conductors which are separated by something called a dielectric or an insulator. So the conductors are obviously the copper wires. The insulator is the insulation material. The thickness of this insulation material and the type of material that it is. So the distance between these two conductors and that type of insulation determine what the capacitance is. So the nominal capacitance of a 1 meter piece of this cable, of J1939 cable between the two conductors, can high and can low, is approximately 40 picofarad per meter. Once again, pico is 10 to the negative 12, so there's a whole bunch of zeros in front of this. So if I had 10 meters of this, I would have the capacitance, I would say that is 400 picofarad if I had a 10 meter long data link cable. So this capacitance and the inductance are what caused that ringing that I had in the signal. This is part of what contributes to that. This is what causes this to be a spike, if you would, to go up and then go back down. Just like a spike or you would see from an ignition coil. It's the same kind of a phenomena, but at a much lower level. The other things that I need to get from this to be able to determine that inductance are what the diameter of the insulation material is, how thick it is, and then how far apart those are spaced, and as well between 18 and 20 gauge wire, the diameter of the wire doesn't change by much, but we can see that anyways, this is what we need to be able to put into a formula to calculate that inductance. So if I go over to a chart such as this, I can put in, there's a big formula that is done behind the scenes. So something like this calculator is pretty cool. 18 or 20 gauge wire is approximately 0.8 millimeters in diameter. If I say I have a 5 meter long data link cable, then each of these wires has this self-inductance. This is in units of henries and nanohenries at that. So nano is 10 to the negative 9th. So if I were to take this and put it into my simulated circuit that I have here, the data link. So this is the CAN transceiver that we showed from the last two previous episodes. If I were to take this and I were to have the two switches, and I'm going to, as best I can, kind of model a 5 meter long piece of J1939-11 cable. And I have my terminating resistors here. I've modeled both of those together. So if you can imagine, this is a 5 meter long cable that has a terminating resistor at either end. We could kind of model it like this. It isn't exact, but it's much more of a better approximation than just wire, where we put no resistance. We said it has no resistance, and we said it has no capacitance and no inductance, but in reality, it really does. So we've taken that capacitance that I figured for 5 meters, it was 40 picofarad per meter. I've taken that, and so 5 meters of this gives me 200. I've taken the capacitance, I've thrown a rough estimate for that capacitance in this, and I can then run this simulation, and we can get something that's going to show us in the time domain something which looks a lot more like what our real signal looks like. You can see our 2.5 volts, we're maintaining it. You can see that we've got a period of time that it takes. This is not a vertical line, and that there's a period of time that it takes for this signal to come up to this value. We also get some of this oscillation. So if I were to model this, and I were to take this and put the the J1939 cable, if I were to take all of these out, this would be a vertical line, virtually a vertical line in the time domain. So I run the time domain situation. If I took all of those, if I took the capacitance and inductance out of it, it would look more like the ideal signal. But the real signal looks like this. Now, the reason if I go over here, why does this have all of this other oscillations? Well, there's a lot of other components that I don't have drawn on my circuit. There are other components typically within the controller. You would have an inductor up front here. You would have some other, this is to minimize the noise that reaches the CAN transceiver. So there may be some additional things, inductors, capacitors, etc., that are here to help filter that signal. That filtering contributes to what we would see in the real scope. The other thing, I have more than one controller on the bus, so all of that capacitance that comes and inductance that comes from those other components that could be on the CAN bus. I might have 20 of these controllers like this on the CAN bus. Each one of these is going to contribute to that capacitance and then that inductance. So the big takeaway hopefully from this is to show that this is, even though this isn't an ideal signal, this is the type of signal that's there in the real world. The challenge is that you'll probably find if you start using a scope or if you look at these signals is, when is this a problem? So there's some point where this noise or this ringing is going to be a problem. There's going to be a point where this time that it takes for the signal to increase becomes a problem. So if things are present which result, if there are failures which result in a change of the circuit resistance, a change of the termination, a change of what this inductance is. Let's say that somebody adds another 100 feet of data link cable. I've seen stuff like this. It's like, well, I'm going to run this way out. And then myself as a test engineer in the past, it's things that I'm guilty of. I've done this because I need to be sitting, at a bench someplace, or we need to have this cable ran outside of the cold chamber when I'm cold starting a machine or something, for example. It's really easy to just take that cable and run it out. But in so doing, I'm inducing and I'm causing this ringing. So the longer that cable is, the more ringing I'm going to have. So this becomes part of the challenge of this. When I need to determine, is this signal a problem or is it not a problem? So that's some of the stuff that we'll talk about in other episodes.